of, I'm going to give a very brief overview of probabilistic sensitivity analysis. We do assume that you kind of have some idea of it, but also, I mean, I think we have enough time. Just feel free to, ask a question. If I can answer it within a reasonable space of time, I'll let you know. Otherwise, I'll have to defer to the end. But anyway, so very generally speaking, probabilistic sensitivity analysis, it tries to overcome some of the shortfalls of deterministic sensitivity analysis, which is that you can only vary your parameter values to a single point or range. So unlike DSA, with PSA, you're able to define a whole probability or distribution of values, and therefore you're able to actually kind of quantify or estimate the probability of your parameter taking on a certain value, given your assumptions of your probability distribution, etc. So I do want to emphasize that it is based on your assumptions that you're using in terms of your probability distribution. It's not magic. It has faults, and it does take, one has to think about what you're trying to achieve and how to relate your probability distribution relates to your data, etc. And it's just important to be careful of those things. So, I mean, for example, like if you are trying to estimate costs, it should always be bounded above zero so that you are simulating from a distribution of costs that will always be greater than zero. And then some very common parametric distributions in standard PSA in health economics is for proportions, you can use the beta distribution, which you have your alpha and beta variables or inputs, and those basically define the shape of your beta distribution and the proportions between two groups. Now, Dirichlet, it sounds scary, but it's basically just a beta, but generalized. So instead of only two groups, you have, 4 or 5 groups. And then relative risk, the common one is to use log normal because it's above zero. Costs, again, gamma and log normal above zero. Quality of life, gamma and log normal because they're above zero. So there are various different ways to actually go about obtaining random samples for your probabilistic sensitivity analysis. But the most common and probably the easiest way is using standard Monte Carlo methods, which is just random sampling based on a distribution of choice. Just a little fun fact, these were actually developed during the Second World War to simulate atoms and basically in the attempt to create an atom bomb, and were primarily developed by John von Neumann, who also subsequently helped develop utility theory. Mad genius, that guy. And then since the area of distributions, when you integrate a distribution, they take a huge amount of time to do analytically by hand. I mean, it probably could take you weeks, if not sometimes years, for some things, depending on how complicated your parameters, etc. With Monte Carlo methods, you're able to do it within a couple of seconds with modern technology, and you can basically calculate the area under the curve. Now, an intuitive way to think about this is you basically choose a shape of a dartboard, i.e. your distribution. Your distribution is the shape of your data in a way. And then what you're doing is you're throwing darts randomly over and over and over again. And eventually this kind of what's technically referred to as convergence basically converges on a point, and it will center its mass in a certain area. So you'll have a higher probability in a certain point of the distribution and lower probabilities towards the tails. And what you're basically doing for PSA is you sampling from that random sample. So again, it goes back to R. Why use R when we can do it in Excel and other languages? Well, in Excel, it's quite convoluted to do a PSA takes quite a long time. I mean, if you have a complicated model, it can take up to 8 hours to sample from. And I mean, that's not even that complicated of a model. Whereas in R, it takes very quick. I mean, basically, it will do this under 4 minutes, 3 minutes. I'll be surprised even on a very entry-level laptop if it takes longer than 5 minutes to do most health economic analyses, PSA analyses. Now, in R, there are various different distributions to sample from, depending on what you want. But the ones that we use start with an R. So, for example, if you want the beta distribution in R, you type R, stands for random, in a way, a random sample basically, R beta, for example. And then every one of these R distribution name functions will start with N. Now, N is the number of simulations you want. So it can be 2, 5, 100, 1,000. Obviously, you want at least 1,000 for it to converge properly. Sorry. But yeah, I mean, you basically want 1,000 samples to get some idea of correct convergence on a distribution. So basically, you want enough dots to be thrown to actually get a proper idea of the shape of what it's going to look like. But anyway, so in R beta, you have your number of simulations, alpha and beta, and this follows again for log normal, R log normal, N your log mean. So that's an important point, is that it's the log of the mean and log of the standard deviation. Your normal distribution, so to randomly sample from the normal distribution in R, you just have N, mean, and standard deviation. And for example, gamma, R gamma, you have your N again, shape, and rate. Now, it's important to just note that in the scripts we've given you, the Darth package has basically tried to make it easier to do a PSA in a more efficient and compact way. And what they've done is they've basically collated all of the parameters into a single function called generate PSA params. Now, am I sharing the screen too? Yeah, you guys can see my R, hey?
Yes, we can.
Okay, perfect. So that's the general function called generate PSA parameters. Over here, you can see it. Yeah, generate PSA parameters. So over here, what's happening is that it's generating 10 samples for every distribution. But I mean, the next question is, where is that coming from? So if you go into the pack that we gave you, you go into the R folder, and then you go into functions. If you scroll all the way down to the bottom, wait, no, not all the way down to the bottom. Sorry, guys. Right. So if you actually go into functions, C, STM, time-dependent simulation, should be in this one, generate, there we go. So in this script here, functions, cohort state transition model, time-dependent simulation, on line 355, there's a function here that wraps up all the parameters that we're going to do a probabilistic sensitivity analysis on. And as you can see here, basically what's happening is you can actually, well, you can do this individually. You don't have to put it in a function. But what this script does is it puts a function into a data frame. So you do putting all your probabilistic samples in a data frame. And they've labeled, the Darth group have labeled, so random transition, random samples of transition probabilities for hull state 1 are equal to a random sample from a gamma distribution. Now, the NSIM over here, we've already defined in the other script. So the NSIM is 1,000, okay? So basically what we're doing is 1,000 simulations. Looks like that. Okay, they just haven't been what's said verbose about what they're assigning it to, but n is equal to n sims. The shape of the gamma distribution is equal to 30 and the rate is 170 plus 30. Those are often, so there's different ways in a lot of health economics textbooks that we're too short of time to go over those types of things, obviously, but in a lot of health economics textbooks and base statistical textbooks is what's often used is called method of moments. And it's basically often it describes equations of how to get from, for example, if you have a mean of costs, how do you translate that, a mean and a standard deviation, how do you translate that into, for example, the inputs for a gamma distribution, okay? So often you have to do that with proportions. How do you convert proportions into the alpha and beta inputs for a beta distribution? So I'm just going to show you here, because I always prefer that to visualize it, is that what's happening over here is we're creating 1,000 simulations of a gamma distribution with a shape 30 and a rate of 200, or 170 plus 30. Okay. You can also visualize that in a different way. Quickly do it this way. Gamma 1,000, 30, 200. Okay. So basically, we're simulating from a distribution that looks roughly like this and is roughly bounded between 0 and 0.3 roughly. Okay, so that's doing the, I think the transition probability from health state 1. Okay, from healthy to sick 1. But if you look here, so if you do that again, and you do max, so your max value is going to be 0.24, so roughly 25% transition probability. It ranges to an 8%, 8.4% transition probability. So instead of having that fixed value, we're going to range over those values. Now, again, the benefits of this in R is that it takes so much quicker, and generally once it's set up, it's so much easier to keep track of. I know it might not look like that right now, but it really is. And so right now, what you can do, again, I'm repeating myself, but if you want, whenever you're doing this by yourself and doing your own model, etc., you can assign these values independently. Basically, you don't have to compile it into a data frame. However, what the staff script has basically done is it's just trying to make it easier and more condensed. Okay, so now that we generate the PSA parameters over here, what we're doing, I mean, already it's done for 10 parameters or more. And there we go. So we have our values for each parameter that we've done a probabilistic sensitivity analysis on. Now, I'm not sure if some of my code is going to work here or not. Let's cross fingers that it does. I don't know why this ggplot's never showing. So that's running. So basically what's happening here is that the only thing that's happening for these data frames over here is that we're just creating an object to store our values from the survival analysis, okay? But the cool thing, again, we're going back to the array, the dynamic array, is that we can extract stuff like the prevalence of disease at a certain time point, the mortality of the disease, etc. But this will obviously take a little bit more in-depth reading in your own time. Okay, so right now, this is where we actually do our probabilistic sensitivity analysis from 587 to line 607. Okay, so we're basically assigning all our values for every simulated value, we're assigning it to these data frames. So we run that. Oh, all right, forgot to run this. So we initialize those values. Okay. Hold on. There we go. I was still thinking with that. Cool. There you go. And this little if statement here in R, that's what's telling, this is what's creating that. So it's basically showing something on the screen and it's saying, okay, well, this is how far it's done. It's just a little progress display bar to keep you updated. Now in Excel, it'll probably still be at about 5%, maybe. Okay. So now we're going to visualize the results. Again, all this code, all it's doing is that we aren't able to explain it in depth right now because it does take time for you to sit down and go through it yourself. But basically what's happening, you're gonna have to trust me, it's basically just assigning values to an object, again, to a list. And it's also assigning specific strategy names, okay, to that list. And then it's also, again, making call names, which is basically just saying the list of the PSA for effectiveness, these are the names for the columns, okay. Here we're defining a willing to pay threshold, willingness to pay threshold, which you can only actually do when you do a PSA. Over here's a little MISC thing where they're defining text size for the scatter plot. See what it does here, and there we go. So that's your cost effectiveness plane. It's really pretty. I'm trying to zoom. And there we go. So right now, it's showing that strategy A and B are pretty similar, they overlap. Combination is more expensive, but generally more effective. And standard of care is quite a bit cheaper, but less effective, even at the extreme values. Okay. And now we get our table here. Again, this is just basically making it so that it's easy to read and you don't have to index everything and do it yourself. It's just making it a more compact, nicer looking way of figuring out what's your best strategy. Okay. So the lowest ISA here is strategy 2, which is strategy B. Okay. Am I reading that right? Someone tell me if I'm not, please. So plot ISAs. There we go. It's also what Federico showed earlier. Strategy A is dominated. Efficient frontier strategy AB is at the top, but the most expensive. And strategy B seems to be the best trade-off in terms of costs and effect. Now your cost effectiveness analysis curves, they're actually a great way to kind of show at what point is your, what is the maximum, at what point, if you're willing to pay a certain amount of money, which strategy should you go for? So what's the probability, for example, here, even though strategy B had the best ISA, if you're not willing to pay at least 80,000, right, then you shouldn't choose this option, basically. Your most effective, cost-effective option up until around over here, which is, I'd say, I guess 65, that's your most cost-effective option. And then it changes to strategy B. And after that, it starts changing again, becoming less, the probability of being cost effective compared to relative to other interventions is becoming less, and strategy, a combination, is starting to increase over there. So that's a really great way of trying to communicate your uncertainty and the probability of a cost, an intervention being cost effective. And again, this is only possible with a PSA, and also with R, it becomes a lot prettier and a lot faster, even though the learning curve can be a headache. So this is your expected loss curves. I'm not going to go into that because that actually takes quite a lot of reading that I haven't even really read or understand yet. And these other curves are all the prevalence curves, etc., that are actually really helpful, which is enabled by the dynamics array approach, where you can actually get specific time points. I mean, to me, that's very visually appealing and easy to communicate. Thanks to Darth, also very easy to implement, relatively easy. So then again, your prevalence, your health states in each health state. And this is, again, this is your basically your error, because it's probabilistic. If it's deterministic, you'll just follow this dash line. Proportional lives, survival curve, and your life expectancy, you can see it peaks at around 40 point something years. Yeah. And I mean, that's about it from me. So yeah. The only thing I would say is that we can break into sessions now if you'd like. To make it easy, I would recommend going into so again, you go into the R folder, your functions, this script here, functions, cohort state transition model, time-dependent simulation, and then you can press Control F or Command F if you're on a Mac, generate _ PSA. It'll quickly take you to line 355. So if you want, I would explore using these distributions, because you can do it directly like this. It's just not as compact. And then what you can do if you want to is you go in here, you change these values however you want to. For example, I've said here in the function script, change the probabilistic cost effectiveness of treatment B. So HR S1 to S2 for treatment B from 0.6 to 0.43. So over here, the effectiveness of treatment B, because it's very sensitive to that. See what happens when you change it, because it's the most cost effectiveness option. See what happens if you put it higher or lower, and then you save this. Remember to press Control S, Command S, or you can, I think there's a save button over here, and then you go back, and you go back up to, I think you have to go all the way back up to line 534 and try run it all the way down to, you don't have to run everything, but you got to run it to about, well, you can actually just press, so then you just go, so 534, and you can just press Control Shift down, and it should select everything for you, and you just run that. Okay. I'm going to stop sharing now. I'm just going to share this. If anyone wants to ask questions here, put here. I don't know if we break into rooms again. I think we do.
Yeah. Yeah, I'm going to stop recording.